15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on the Space Nuts podcast. And if my mathematics is correct, this is episode 191, but I might have missed one. I didn't check. I'm pretty sure it's 191. My name's Andrew Dunkley, and with me, as always, is Professor Fred Watson. We're always so professional, aren't we, Fred?
Look, certainly last week you said it was 190. So that, there's a bit of logic there that implies that if that was correct, then this week is 191. I can relate to that.
It was my weakest subject at school, though. So I could be wrong.
Never mind. The subplot to this is, but who's counting?
Yes, exactly. Well, someone is. Actually, I think Apple Podcasts requires us to count.
Oh, do they?
Yeah, they require episode numbers.
As far
as I'm aware. So that's why we've had to number them.
Well, I didn't know that. There you go. Well, 191. Makes me think you'd get a life, doesn't it?
I was about to say the same thing. I think we've used that joke before. We'll try a new one next week.
Yeah,
Coming up in this episode, we are going to talk about Jaxa, the Japanese space agency, or a small dog, not sure which, planning a mission to the moons of Mars. I think specifically Phobos. Could be wrong about that, but there's only two. So we'll talk about that. We'll also talk about the discovery, thanks to the Juno mission, of water in the atmosphere of Jupiter, which has got everybody excited. I suppose finding water anywhere outside of Earth is exciting. And we've had a couple of really fascinating questions piped through to us. One from Justin Holland, who wants to know about the Roach limit. I went to school with a kid named Roach, so that could have something to do with it. And one we've spoken about before, but Sven Wolsgaards has messaged us from Belgium, wanting to talk about the Drake equation and how accurate and reliable it is. And that's the equation that determines, the probability of life beyond Earth or in the universe in general. So we'll look into that. Now, last week I told you I wanted to get you to go on a mission with me to title my new book. So at the end, I'll explain the basic plot of the story without giving too much away and see if you can come up with a title. And I promise whoever comes up with a title, should I choose to use it, will get a credit on the inside cover. So that's the prize. Can't offer you money, don't have any. But a credit in the book. If you're happy with that, I'm more than happy to put your name in the cover for coming up with a title for my new science fiction novel. It's not a long one. It's actually quite a short novel, Fred. It's only about 50,000 words or thereabouts. Yep. But I've read some articles about writing, and one of the questions someone asked was, how long should my novel be? And the answer is, as long as it takes to tell the story. So there you have it.
Profound.
It is profound. It's very deep. So this one's only half as long as my last one. So it'll be a quick read, but I hope people will enjoy the story. Lots of twists and turns. I really enjoy trying to keep people guessing. But no keeping people guessing about the Jaxa mission, because they are dead set serious about heading to Mars and taking a quick left at Greenland and ending up on Phobos, I think it is, or one of the Martian moons.
Indeed, that's right. So, I'm very glad to have pulled this story out, because I know Mars is your favourite planet. And whilst Phobos and Deimos are not part of Mars, well, they're certainly very closely connected to Mars. So they're in orbit around the planet. They were discovered in, if I remember rightly, something like the 1880s, something of that sort, with a strange connection to Pluto. This is coming from the depths of my memory here, because let me get this right. I've written about this, but it was a long time ago. The discoverer of Phobos and Deimos was, I think, related to Venetia Burney. Venetia Burney was the 11-year-old Oxford schoolgirl who gave Pluto its name.
Oh, okay.
So there's a factoid that you didn't want to know. I should check it. It's in one of, I can't remember which book it's in. It's in one of my books. I think it might be in Stark Raving Mad. But yeah, it's a very nice connection there. A nice little link between the moons of Mars and the dwarf planet Pluto. And that's the end of the story, really, isn't it? No, it's not. Well, there is more. So Phobos is a really interesting world. It's about, if I remember rightly, about 30 kilometers across. It's got a curious internal constitution. It's very, very low density, and the suggestion is that it's like a piece of pumice. It's porous, and I'm not sure that we actually understand the reason for that. In fact, it's probably got echoes of. Now, which of is it Epimetheus? No, it's one of might be Hyperion. One of Saturn's moons has a similar, composition. Very, very lightweight, almost porous in the sense that it would float on the surface of water. So, very interesting place. Also, has been suggested as a possible landing site for humans in their exploration of Mars. And of course, the great thing about landing on a world like Phobos is that you don't need the huge amount of energy to get your astronauts back off the surface of a planet. So, getting off the surface of Mars is, well, it's certainly less of an effort than getting off the surface of the Earth, but it's not that much less. The gravity is about 1/3 of Earth's. On Phobos, though, you have an escape velocity of 40 kilometers an hour, which means you could get off Phobos in a Toyota Corolla.
I was going to say, yeah.
Or even on a bicycle, probably.
Well, actually, the fastest I've ever ridden a bicycle is 40 kilometres an hour.
Well, there you are. Yeah. So if you'd done that on Phobos, you'd be on your way back home by now, in big trouble.
Or somewhere.
Yeah.
So I'd probably be able to catch that Tesla and drive that home instead.
Yeah, that's right. Yeah, you might be able to catch it on the inswing. Really interesting world. And there has been, in the past, an attempt to send a probe to Phobos. This was a heroic event, heroic effort, I should say. Back in 2011, the Russian space agency, Roscosmos, launched a spacecraft with the slightly unappealing name of Phobos Grunt. And it was called, so Grunt is just the Russian word for ground.
Yeah.
It's the Phobos lander, I guess. Phobos Grunt was launched on the 8th of November 2011, but never made it it went into a parking orbit around the Earth with the idea that it will be boosted into a Mars transfer orbit to head it off to Phobos. But things went wrong. It never. I think the transfer orbit rocket never fired.
It didn't have enough. It didn't have enough grunt.
Grunt, exactly. See, I set that one up for you, Andrew.
Sure did.
So it didn't have enough grunt because I think the motor didn't work at all, and that temporary orbit that Phobos Grunt was in around the Earth was a very temporary one. It was not sustainable, and so the following January, 15th of January 2012. It actually re-entered and burned up in the atmosphere. It's a big spacecraft. I think it was about 13 tons. It was, it's such a tragedy that did not work because.
And the first words from Mission Control were, "Did I forget to give you the fuel card, Dmitry?"
Yes, right. That sounds like a page out of your new nameless book.
No, it's not.
No, right. Anyway, so as I was going to say, it would have been fabulous if the mission had been successful because it's such an interesting place. When you look at pictures of Phobos, it's like this, almost like a piece of fruit in its shape, but it's got this enormous dent in it, which is a crater called Stickney. It's one end of it is just basically a huge crater, actually with several other ones inside it, smaller ones. But the other remarkable thing is that emanating from Stickney are all these grooves in the surface of Phobos, which I guess come about because of the debris. When that impact crater was formed, the debris was splattered all over that little world. So, okay, to cut to the story, Jaxa, the Japanese Space Agency, has just announced that their MMX mission, which is Martian Moon Exploration, great name, Martian Moon Exploration mission, it's got the green light, basically, and will launch probably in 2024. In fact, September 2024 is the expected launch time. The plan is to have an orbiter, which will basically orbit Mars and the Martian, the Martian moon system. I think it will also go into orbit around Phobos. So as well as orbiting Mars itself, it'll orbit the moon, I think. But there is also a lander. So we will expect to see images from the surface of Phobos and possibly even a rover. But the big, I guess, the really cool aspect of this is the possibility of a sample return when the spacecraft comes back Actually, it will leave Mars. The plan is 2028, August, leave Mars, get back to Earth 2029, September. Of course, these dates are defined by the relative orbits of the Earth and Mars. There are only certain windows where you can actually make the transfer between the Earth and Mars. So the possibility of bringing back something from the surface of Phobos. And of course, in doing that, Jaxa will build on its experience with its Hayabusa spacecraft, the two of them, which basically returned, one is still on its way back, returned samples from asteroids. The first one, that well-known asteroid, Itokawa, that was back in 2005. And more recently, last year, Hayabusa 2 visited an asteroid called Ryugu. And we expect the samples from that asteroid to come back to Earth late this year and will land here in Australia at Woomera. So that is a great experience for the Japanese Space Agency. It's learning how to do this sort of thing. And they will no doubt bring that expertise to bear when the mission to Phobos takes off in 2024. And I hope you and I will be able to talk about it, Andrew.
I hope so too. You talked about the size of Phobos at around 30 kilometres. Is it possible it's a captured asteroid rather than our moon, which seems to have been created by an impact and ejected from the planet and forming around the parent planet? But is it possible that Phobos and Deimos are completely different types of objects to Mars itself?
Yes, I think that's a well-made point. And of course, Mars is the orbit of Mars is on the inner edge of the asteroid belt. So asteroids that tend to cross the orbit of Mars might well be captured. So they're tiny objects. Deimos is even smaller. I think it's only 10-ish kilometres or something like that. Nothing like our own moon. So I think captured asteroids is probably the way they're viewed, and that might explain why Phobos has got this peculiar construction or constitution. Why it's not a solid world like most asteroids are. It's a very unusual little world. We probably won't know much about its origins until after we get these samples back from Phobos in 2029. So that's only 9 years away. It's not that far. When you think of what we were doing in 2011, which is 9 years ago, that seems very recent indeed.
Yes. So the mission's purpose is obviously to learn as much as we can about Phobos and how it is there, why it is there, and what it is made of, and why it's hollow, and also to give Jaxa some more experience and learn from this and, move on to bigger and better missions, I guess.
Yes, that's right. And actually, on that point, it's an international collaboration as well. So the Japanese Space Agency is responsible for the spacecraft and doing all the orbital maneuvering and all the rest of it. But there are a number of international partners too. So there are 11 instruments on board MMX, 4 of which will come from partners in international consortia, including NASA, European Space Agency, the French Space Agency, CNES, and DLR, the German Space Agency. So that these are all, like guest instruments almost on board the spacecraft. Jaxa will also provide instruments, including basically a telephoto lens, a narrow-angle camera, which will give us, I hope, stunning pictures of the surface of Phobos, and all kinds of other instruments, including a laser altimeter, a dust monitor, a mass spectrum analyzer, so we know what charged particles there are around those moons, and of course all the equipment required to take the sample and bring it back. The website, the MMX website, says that the spacecraft, when it lands, it would land for several hours to collect a sample of at least 10 grams using a corer that can gather material from a minimum of 2 centimeters below the moon's surface. There you are. So
very
that's
good.
the plan.
Interesting. And most importantly, a low fuel warning light. I'll need one of those.
Yeah, come on, you've got to do another grunt joke somewhere in there.
I'll save
Hopefully it'll have enough grunt to get there. There you are.
Yes. Well done, Fred. That was a good one.
Don't give up your day job. Yes, I know.
I wasn't going to say that.
No.
Not at all. You're listening to Space Nuts, and we certainly are a bit nutty today with Andrew Dunkley and Fred Watson. Let's take a break from the show and hear a word or two from our sponsor, Grammarly. Now, I have to say I'm a big fan of Grammarly because I've been using it for a few years now. Very helpful for authors, but also really good for everyday life. They've saved me on a few occasions, particularly with spelling, but also with a few issues that didn't quite make sense. It's built by linguists and language lovers, and Grammarly's writing app finds and corrects hundreds of complex writing errors, so you don't have to do it yourself, word by word, day by day. You can easily copy and paste any English text into Grammarly's online text editor, or just install Grammarly's free browser extension for Chrome, Safari, Firefox, and quite a few others. Grammarly's algorithms flag potential issues in the text and suggest context-specific corrections for grammar, spelling, and vocabulary. Grammarly explains the reasoning behind each correction so you can make an informed decision about whether and how to correct an issue. Grammarly helps you write mistake-free Gmail, Facebook, Twitter, LinkedIn, and nearly anything else you write on the web. For you, the listener of Space Nuts, Grammarly is offering a free download of the Grammarly software. So if you'd like to download Grammarly today, go to getgrammarly.com/spacenuts. Again, that's getgrammarly.com/spacenuts to download Grammarly for free and let them know you came from us. I'll include the link in the show notes as well. And now, back to Space Nuts.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, very excited to say that our YouTube numbers have soared. It turns out I've been misreading the numerical device on the YouTube page. So when I said we'd gone up from 1,004 to 1,006, that was 1,040 to 1,060. It's now 1,100. So it's steaming ahead in leaps and bounds. So thank you to those who are following us on YouTube. And it's as easy as just doing a search on your YouTube page using Space Nuts. Although I do believe there is a Space Nuts movie, nothing to do with us. I would just make sure you get the right Space Nuts if you do the search, but I think it'll be pretty obvious our Space Nuts logo's there, and I think those two space people represent us, Fred. I'm not sure. I haven't asked my brother what the concept was, but anyway, thank you for supporting us on YouTube, and if you'd like to follow us on YouTube, that would be wonderful. Now, Fred, we're going to talk about water in Jupiter's atmosphere. Now, this is evidence that's come about from the famous Juno probe. They've done an analysis, and they're very, very excited because I guess finding water anywhere outside of Earth is exciting. It's starting to become all too common, but finding it in Jupiter's atmosphere, I suppose, is a little bit of a surprise.
Yes, it's not kind of rainwater. It's basically the molecular construction of Jupiter's atmosphere. So these are water molecules in vapor form, effectively.
Okay.
It's a really interesting story, this, that I have to say I was not really familiar with until this news item came about. But it goes back to the 1990s when the Galileo probe, which was a famous NASA mission to Jupiter, actually investigated, among other things, the water in Jupiter's atmosphere. And the way these spacecraft do that is by basically counting oxygen and hydrogen atoms, which, of course, are the constituent parts of water. Galileo, when it entered Jupiter's atmosphere, which it did to basically burn up at the end of its mission, because like Phobos Grunt, Galileo was running out of fuel, and the mission controllers, as always in these situations, destroyed the spacecraft by burning it up in the planet's atmosphere rather than risking a crash landing on Europa, for example, which may have microbial life. And so we get that mixed up. So Galileo hit Jupiter's atmosphere and kept transmitting data down to a depth of about 120 kilometers. It's extraordinary that, you could still work at that sort of level.
Yeah, the pressure would have been immense there.
It would have been, yeah, that's right, getting very high. So, but what they found in doing that was actually 10 times less water than had been predicted. They found very low levels of water. And another puzzle is that the deeper they went, the more water seemed to be there. So there was not much, but it seemed to increase as the Galileo space probe descended into Jupiter's atmosphere. And this flies in the face of what planetary atmospheric scientists think should be happening, because that at that depth, 120 kilometers into Jupiter's atmosphere, they were expecting a very, very well mixed composition. In other words, so it shouldn't have increased as it was going down, because it was so well mixed that it should have been basically a constant level. So that was a puzzle. But now we've got information from the Juno probe that actually sort of overturns that surprise. So Galileo seemed to find Jupiter's atmosphere drier than expected, whereas actually now the Juno probe has turned it over and found that it's about 3 times wetter than expected. Oh. It's still very little. It's only about 1/4% of the molecules in Jupiter's atmosphere. So that's a tiny fraction. It's telling you that 1 in every 400 molecules is a water molecule, which is not much, but that's still more than expected, because it's more than what we call the solar abundance of hydrogen and oxygen. So there are many questions that raises. One of which was, well, what was wrong with the Galileo data? And I think there was evidence that, and this comes from ground-based observations around the same time as Galileo was making its death plunge into Jupiter's atmosphere. Ground-based infrared observations seem to suggest that Galileo had accidentally hit a spot where the water vapor levels were low. So, yeah, and once again, that suggests that the water's not well mixed when you look into Jupiter's atmosphere. And the results that I've read suggest that the first 8 flybys of Juno, they're now coming back up to date, around the planet Jupiter, also showed a lack of mixing. They use the radiometer on the spacecraft. This is basically a device that measures. Usually it's microwaves actually that you're measuring. That's probably right because water molecules emit in the microwave region. They penetrated down to 150 kilometers and found. Once again, a lack of mixing. But they also highlighted, because Juno is not like Galileo, which was just plunging into one part of Jupiter's atmosphere. Juno's in orbit around Jupiter. So it can make many measurements, but it also seems to suggest that there's more water at the equator of Jupiter than elsewhere. So we've got a quote from Scott Bolton, who's the Juno principal investigator at the Southwest Research Institute in the USA, one of the great planetary science centers. He says, just when we think we have things figured out, Jupiter reminds us how much we still have to learn. Juno's surprise discovery is that the atmosphere was not well mixed, even well below the cloud tops. And that's a puzzle that we're still trying to figure out. No one would have guessed that water might be so variable across the planet. Did you guess that, Andrew?
Well, it made me wonder because it's variable across Earth. We have vast oceans. We have deserts where there's very minimal water. We have it in solid, liquid, vapor and gas form. And so, if aliens dropped a probe on Earth and landed in the middle of the Sahara and they did some analysis, they go, not much water there.
Yes.
But could that be the same for Jupiter?
Well, that's right. I suppose what the scientists, and these are people who know far more about planetary atmospheres than I do. In fact, I've got the Nature astronomy paper in front of me, most of which I don't understand. It's entitled "The Water Abundance in Jupiter's Equatorial Zone," and it's got a long list of authors published in Nature Astronomy, I think this week actually. And anybody can go and have a look at that. But it's very, very technical. So I think the point about this mixing is that we believe that once you get below the surface layers of Jupiter, below the cloud layers, what you're faced with is something that is more like a star, the interior of a star, than the interior of the atmosphere of a planet. And I think that's why this idea of well-mixed gases comes from. So, and it may also be, one of the things that we do in astronomy, because we often don't have too many lines of evidence to go on. One of the things that we do is make simple assumptions about things. Like, for example, we make an assumption that the universe is isotropic. That means it's the same in all directions. Now, to the best of our observational abilities, that's true, because everywhere you look, the universe is essentially the same. Of course, there's detail differences, there's galaxies and clusters of galaxies and all of that sort of thing. But generally, it is isotropic. And I think planetary atmosphere scientists probably do something similar. They probably say, OK, we'll assume that the atmosphere is well mixed, and then they do calculations based on that and look at how that compares with observations. And it may well be that assumption of a well mixed atmosphere is just not one that holds water. They would have good reasons for believing that. It wouldn't be just, this is the easiest way to do it, although it is the easiest way to do it. But you'd also, you'd make logical deductions about it. So the really interesting piece of work. I'd like to read more about this because, as I said, it's it is quite complex stuff. But to the experts in the field, the planetary scientists, it is a surprise, and I think creating rather a lot of excitement. Just one footnote to the story, Andrew. Why is it important to know about this, and why is it exciting people? It's because it's all about how solar systems form. It's about how planets like Jupiter, the dominant planet in our own solar system, how that forms, how the molecules that were present in the protoplanetary disk, how they wind up in the atmospheres of planets like that, because this plays into our understanding of other solar systems, of which we now know very many.
Yes.
far more than we knew when Galileo was visiting Jupiter.
Indeed. All right. And yeah, I guess there'll be more to learn from the Juno mission. They keep analysing all this data from all of these amazing missions. And there might be another announcement in the not too distant future, I imagine. Yeah. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, if you'd like to become a patron and support our podcast with a few dollars a month, you can do that at patreon.com/spacenuts. A few more people signed up last week. Thank you. We really do appreciate it. As a patron, you get an early edition commercial free of the Space Nuts podcast. You get bonus material on the Patreon page. And, you're supporting our podcast and keeping us afloat, which we certainly appreciate. So patreon.com/spacenuts if you're interested in becoming a patron. A mere $3 a month, I think, is the minimum, but it's up to you, really. You can put in for as much as you like or as little as you like, which, we're not going to stand here and demand cash. It's not the way we work. It's optional, but you might like to do that. Now, Fred, we've got some mail to sort through. I'm just dipping my hand in the bag right now, like they used to do on those afternoon TV shows that the kids wrote into so that they could have their favourite cartoon put on TV or whatever. Our first, and of course we do it that way because we're not real high tech, so we only accept letters by standard post. Not true. But we've got a message from Justin Holland, who has got a few thoughts about the roach limit. Justin, thanks for your question. I hope all is well. Yes, it is. Thanks, Justin. While reading today about a hot Jupiter planet that is getting too close to its parent star, exoplanet NGTS-10b, with an orbital period of 18 hours, I was pondering the language used to describe the event. It seemed to infer that the roach limit as some fixed distance relative to the mass of the star or other stellar parent object. I can understand the roach limit being at what is effectively a fixed distance when the satellite is a relatively small object compared to its stellar planet. But in the case of a hot Jupiter orbiting a star, we could be talking about a satellite that itself is not far short of being a brown dwarf star. My question is this: wouldn't the roach limit actually be a function of the mass of both the stellar planet and its satellite, in much the same way as the barycenter will change with the relative mass of orbiting objects? Ooh, he's put a lot of thought into this one, Fred.
Yep.
First of all, you better explain the roach limit to me. I'm sure everyone else knows what he's talking about.
Actually, I might cut to the answer.
Oh, okay, that'll make it quick.
And then, well, it is, because the answer is yes. A great question from Justin. So what is it's usually called the Roche limit. It's named after Edouard Roche, who was a French astronomer, and he deduced this thing back in 1848. So it's been around for a long time. He's in the field of celestial mechanics. What's the Roche limit? It's, if you imagine a massive object like, for example, the sun, and then you have something small like a planet or smaller like a planet, and put it closer and closer to the massive object, you must get to a point at which the tidal forces, and by tidal forces I mean the inequality of the gravitational pull acting on one side of the planet compared with the other, because that's how tides work. It's an inequality of the gravitational pull on one side compared with the other side. So that inequality, at some point, as you get closer and closer to the star, is going to eventually pull the planet to pieces, because its internal strength has only got limits on it. And if you've got gravitational forces bigger on one side of it than the other, you're going to get a demolition. And that happens at the Roche point, or the Roche limit. Okay. It's important in astrophysics because there are some objects that we know are within the Roche limit of their parent, of the bigger object that they're in orbit around. This is often things like supergiant stars and dwarf stars. And so you get something called a Roche lobe. And the Roche lobe is that area of space which has got the debris of the smaller object in it, or that volume of space, I should say. So very much, an important aspect of astrophysics. Now, Justin's question is right on the money, because he's saying we usually just quote the Roche limit for the parent object, because the smaller object, and he's talking at the moment about an exoplanet. So you've got a sun with an exoplanet around it. The exoplanet has a much lower mass than the sun, so we would normally just talk about the Roche limit of that sun itself, in terms of how near this exoplanet could get to it without being pulled to pieces.
Yeah.
So, but Justin's question is, well, surely it's a function of the mass of both of them. It's not just, the bigger object. And he's right. It actually is slightly more, a little bit more subtle than that, because when you look at the mathematics, it is actually the ratio of the densities of the two objects that comes into play. But you can rearrange the equation, which makes it the masses of the objects as well. So it's not often we throw equations into these debates, and I'm tempted to do it, because d is the distance of the Roche limit from the parent star. There's a function Rm, which is the radius of the smaller object, and capital M is the mass of the primary object, small m is the mass of the secondary, and the equation is d equals R into 2m capital M over small m to the power 1/3. That's the way the equation works, and you can see that the masses of the two objects come into that. Okay. So it's a very esoteric point. I think that's the first equation we've stuck into a space nuts broadcast, apart from E equals mc squared, which we throw around all the time.
Oh, yeah. Well, but yeah, that one prompts a question in my mind: is there a Roche limit between Earth and the Moon?
Yes, there is, and I don't know what the distance is, but if you brought the Moon close enough to the Earth,
3 inches.
It's probably I don't know. Let me just hazard a guess. Probably not that much different from where all the geostationary satellites are, which is 36,000 kilometres. So that would be 10% of its actual distance or thereabouts. I should calculate that. It's a really good question.
It's irrelevant because it's actually going away rather than.
It is going away. That's right. But yes, there would be if the Moon decided to come the other way, there would be a point at which it would fall to bits, and that would be. It wouldn't be very nice, really, because I quite like the Moon.
Yeah. Would it be catastrophic for the planet?
Yeah, I think so. Yeah.
I imagine it would be. All right. So we got that one covered. The answer is yes. Simple.
The answer is yes. That's right. So Justin's absolutely right. It's a function of the mass of both the objects.
Excellent. Well asked, Justin, and well answered, Fred. Let's move on to our next question. This one comes from Belgium. Sven he wrote it phonetically for me. Sven Walscards, I think is how it's pronounced. Hi there. He's got a bit of a tongue-in-cheek thing going here at the moment. Seems like you even had fans of your podcast in Belgium. Of all places, that not very exotic nation in the middle of Europe's economic desert or sea of indecisiveness, whichever you like best. Luckily, we also have good chocolates, beer and fries. Yes, you do. I have witnessed them all, and yes, don't be too hard on yourself, Sven. I would like to know your opinion of the Drake equation. Could it be sound, or is it just useless? And in what spectrum of the Fermi paradox would you position yourself? I, for one, don't believe we could be unique enough to be the only living creatures in the vast universe or even multiverse. A last question that has absolutely nothing to do with the previous. Would we plan to go to the Moon, or should we properly plan to go to Mars instead, even if that could only take a few years more of preparation? Thanks, Sven. 3 questions for the price of one.
For the price of one, yeah, that's right. Let me put in a totally irrelevant aside here. Mm-hmm. Because I'm really grateful to Sven for giving us the phonetic pronunciation of his name. He's written it as Walscards. you probably are not like me, Andrew, immersed in 19th and early 20th century engineering, but I was, and spent my life interested in all kinds of engineering, particularly where it came to steam engines, because steam drove everything when I was a kid. The trains, all the ships, lots and lots of other things. So I was fascinated by steam engines. And steam locomotives, pretty well throughout the world, have what's called a valve gear. This is the mechanism that opens and shuts the valves of the cylinders, which was invented by a Belgian gentleman with the same surname as Sven. So this is spelled Walschaerts. And all the steam buffs that I've ever talked to in my 70 decades of life have pronounced that incorrectly because we've always made it German and called it Walschaerts. But Sven is telling us it's Walschaerts, and I can believe that because Belgian pronunciation is very different from German pronunciation. So thank you for setting me right. I shall share that knowledge with the only person in. Actually, there are two blokes who I'm in contact with here in New South Wales who also know about that valve gear. Nobody else does, apart from all the steam guys.
Now, all three Space Nuts listeners know.
Yes, that's right.
Notice I've promoted it from 2 to 3 over the last 12 months.
Well, that's quite correct. Yes, apart from the 1100 on
1100 on YouTube.
Yeah, who have now switched off and cancelled their subscriptions because they don't want to know about steam engines. However, the Drake equation is what Sven is asking about, and it's a great question. And in fact, I don't think it's useless. So, okay, Frank Drake, 1961, I think it was, when this equation was put together. Let me cheat and read a passage from Cosmic Chronicles because I wrote this, so I can say it.
And it's available in the Space Nut shop.
It is. The equation attempts to estimate the number of intelligent civilizations in our galaxy by looking at a series of factors, such as the rate at which suitable stars form, the fraction of those stars with planets, the number of those planets suitable for life, and the number on which life actually appears. Then you factor in the fraction of life-bearing planets on which intelligence emerges, the number of those that produce technology capable of emitting signals into space, and the fraction that actually go ahead and do so. As I said here, most of those factors are just guesses, although at least we now know that most stars do have planets. But so it's a useful exercise to think about that, and that's why the Drake equation has been such a well-established and popular aspect of astrobiology. And
it works because at the moment it still has an answer of 1.
Well, the probability of 1 says that yes, what you're trying to do is work out the fraction of civilizations that might be emitting signals compared with the total number of stars, for example, in the galaxy. And that's a very much smaller number than 1. But we know of one civilization that, you're quite right, that there's only one place in the universe where we know intelligent life exists, if we can call it that.
Well, that's debatable, but yeah, carry on.
Is capable of emitting signals. So the thinking in astrobiology, and this is actually where why I put the Drake equation into this final chapter of Cosmic Chronicles, is that, yes, I think we might find that microbial life might be relatively common. We don't know. That's just a guess. But it's based on the fact that here on Earth, we find microbial life in every nook and cranny of the planet. In the atmosphere, in the rocks, in the ice in Antarctica, we've got, life is abundant.
Yes.
And that suggests that if you have the right conditions elsewhere, and there are plenty of places where there are conditions not too dissimilar from what extremophiles, these are the extremes loving microorganisms like on Earth, then maybe life is abundant throughout the universe.
I suspect it is at some level.
Yes, that's right. So that's rudimentary life. But the fly in the ointment, and this is where the thinking, I think, has hardened up a little bit in the last maybe the last 10 years, that there is such a big jump to get from that state of living organisms to multi-celled organisms. And a number of people have, pointed to the kind of thermodynamics of the situation, that you need a huge amount of energy to make that transition to a multi-celled organism and then to evolve from that. And so I think the thinking now is that it may actually be a very rare step to get from a microbe to a prawn or something like that, or some other fairly low-level organism, and then to develop intelligence, very, very much more rare again. And so, the thinking now is that maybe when you multiply all these factors together, in particular the number of life-bearing planets that evolve intelligent life, then you've got a very small number indeed. And actually, the reason why the Drake equation, why I could quote that little bit from Cosmic Chronicles, is because I was discussing an Oxford University study that's looked in detail, and what I've said basically is that with the very best current estimates, this new study from Oxford University indicates that there are unlikely to be any other civilizations within the observable universe. Now, what they say, that paper actually says there might be other civilizations, but they're so far away from us that they might as well not be there, because we're too far away for any kind of contact. And so, that actually then solves you the problem of the Fermi paradox. The Fermi paradox says, where are they all? The idea that if you've had 1 million years of evolution for a civilization, and that they become a spacefaring species, their evidence should be all over the galaxy, but we don't see any evidence whatsoever. So the Fermi paradox is very neatly solved by the idea that these species are either too far away to ever make it in our neck of the woods, or they're not there at all. Which in itself, I think, raises some really interesting philosophical questions about ourselves, because we might be the only species, certainly in our part of the universe, capable of thinking about the universe. And that says that there's an awful lot of stuff out there for just one bunch of folk with intelligent, with the brain power to contemplate the universe. It's an extraordinary and rather disturbing situation. I haven't really got my head around that.
Yeah,
properly.
and it opens up all sorts of questions, and it starts to bring religion into the
yes, it does almost
into the argument. I did talk about this once, believe it or not, playing golf with one of my playing partners, and he said, it brings it down to faith. Yeah, okay, but he said, one question you should ask yourself is, how is their existence? And no one can answer that.
No.
How is their existence? We know we're here. We talk to each other. We communicate. We see there is a universe. We see planets and moons and stars and nebula and galaxies. But how is their existence? Not why. How is?
So how? And that question can equally be applied to the universe itself.
Yeah.
How, we in cosmology, we've got a pretty good idea of what happened in the aftermath of the Big Bang, which is certainly a real event. But that in itself raises all kinds of questions. And there's a paper which I haven't read yet that's been on my desktop for the last week or so, which is about the idea that yes, the universe could come into being from nothing, which is certainly an idea that's been proposed over a number of years by some quite expert cosmologists. But it's all very interesting stuff, very hard to get your head around. What's much easier to... Sorry, go on, Andrew.
I was going to say, and I suppose quickly we should go into part 3 of his question
that's right.
about should we go to the moon again, or should we plan, take a few extra years and go to Mars instead?
Yes, so that's a question that's a lot easier to get your head around.
I think we should do both.
Yeah, that's what's going to happen. So the moon is going to be really a staging post. There's a project called Gateway, the Gateway project, to provide a kind of orbiting gas station around the moon. And NASA certainly has has the mandate to put the first woman on the moon and the next man on the moon by the middle of this decade. And that will be a stepping stone to Mars. So you really have to do both. It's a learning process. There are many big technical problems involved in sending humans to Mars, which we haven't really solved yet. So it's an ongoing thing. So maybe the best guess is the moon, walking on the moon again by 2024, 2025. Walking on Mars by 2035, perhaps.
Yeah, well, we have to go to the moon because somebody lost a golf ball there, and golfers hate losing golf balls. So they've got to get that back. But yeah, you're right. Sven, thank you so much for your questions. Very insightful and really fun to talk about, and certainly doesn't really answer the question of life, the universe, and everything. But it's fun to try and figure it out. Now, one more thing before we go, and we've used a lot of time today, but I hope you'll indulge me. I've just finished writing my latest science fiction novel, Fred.
Now, the nameless novel.
I am struggling for a title. I really am, and I'd like someone to come up with something. Now, the basis of the story is you've got three different races of people. The focus is on a race of people from the Andromeda galaxy, and they're invaded. And they can't win. So they decide the only way to save themselves is to send out 7 fleets in 7 directions to 7 potentially livable planets. And we focus on one, the first Andromedan fleet, who've identified a planet. And along the way, something catastrophic happens and ends up only the flagship arrives at the destination to horrifyingly discover that not only is it occupied by a race called the Turanians, they're very intelligent and advanced, and to the greater horror of the Andromedans, their sworn enemies are already there. So you've got this convergence of 3 races, and the Andromedans want to take basically settle on Turania. They've run into this race of rather destructive creatures called the Borsch, who have systematically wiped them out. So there's no trust here. And you've got this sort of 3-way situation going on where all are negotiating with each other over the future of the Andromedans. My brother said, call it Andromeda. I said, but it's not about Andromeda. They're not even there. They've left. They're parsecs away. So, it leaves me pondering a potential title. I thought, call it Turania, but that doesn't really say anything. I want to come up with sort of a hooky type of title that will make people go, wow, what's this about? So that's the basis of it. You've got a race running away from an assailant type race. They find a planet that they can live on. Turns out it's occupied, and lo and behold, the bad guys turn up as well. So that's the scenario.
There you go. Okay, I'll throw in my 10penneth.
Yes.
There was a movie called Contact.
Yes, I'm aware of it. I love it.
But this is about wheelings and dealings and people beating each other up. It maybe should be called Contract. Because that's what you want at the end of it.
Well, believe it or not, that is part of the basis of the story.
Oh, there you go.
Yeah, there is wheeling and dealing that goes on. But yeah, I can't say much more because I'll give away a few of the hooks and the twists. But yeah, there's a certain lack of trust going on in all of this as well. So if anybody can think of something, send me a message on Facebook. That would be the best way. I might actually post on the Space Nuts Facebook page the same question so that you can maybe answer it, and I'll keep an eye on it. If I like one enough to say, yeah, that'll be the title, I'll give you a credit on the inside cover. That's all I can offer. It's a low-budget production.
Yeah, that's all right.
Yeah. But there it is. So we'll see how it goes. You've got the Andromedans, you've got the Turanians, and you've got the Borsch. The Borsch are the bad guys. Well, that's what I want you to think. They might not be.
Ah, there you go.
They could be, though.
Wheels within wheels, contracts within contracts.
Yes. So, and I, as I was finishing it, I kept coming up with plot twists. So, and I thought, you know what, I'm just going to keep going till I run out of ideas. So I put them all in. Every single plot twist. It turns around at the end like nobody's business. So if you can figure it out, good luck to you. But I hope it's a fun read. Anyway, we better leave it there, Fred. Thank you so much. It's been a lot of fun.
As always, Andrew. Good stuff, and good to hear about the new book, whatever it's going to be called.
Whatever it's going to be called, but it needs to be uploaded by the 31st of March. So there's my deadline.
Okay.
Which also happens to be my birthday, so that's a nice day.
Yes, that's right. Well-known date. Yes. Well, thank you very much, Andrew. Thanks for putting up with me again for another week, and we'll speak again soon, I hope.
We will. Professor Fred Watson, half of the team that makes up Space Nuts. Well, actually, it's probably 1/3 because Hugh does all the production. You just never get to hear his voice. He's an old radio man, and when I say old radio man, he's old and a radio man. Sorry, Hugh. And we'll catch you next week on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.